I'm so glad you're here. Tonight, we're going to take a quiet stroll through the subtle, soothing mathematics of the natural world. From the spirals in sunflower seeds to the branching of trees and the frothy chaos of clouds, we'll uncover how nature seems to hum with hidden patterns. It's a world where numbers gently guide the way leaves unfurl, where storms swirl with symmetry, and where even the way rivers meander has a secret geometry behind it. Now, I should warn you, this might be just interesting enough to keep your brain quietly curious. If you find yourself wide awake, wondering why pine cones spiral the way they do, I can only apologize. But if you're going to lose sleep, at least it will be in the noble pursuit of understanding why ferns look like mathematical poetry. Before we get too far in, may I kindly ask, if you enjoy this slow and curious journey, please consider giving this video a like and subscribing to the channel. It helps more sleepy seekers like you find their way here, and if you feel like it, let me know in the comments where in the world you're watching from, and what time it is for you right now. I always love hearing how far these quiet evenings reach, so snuggle in. Let the day fall behind you like a leaf on still water. There's nothing to do now but drift gently through the calm, quiet beauty of numbers in nature. And just a gentle reminder, this video is for educational and relaxation purposes only. Nothing here is intended as medical advice or a substitute for professional care. Now, let's begin. Let's begin with something you've likely seen before, a sunflower. You've probably admired its bright yellow petals, its sunny disposition, maybe even its tall, proud stance in a summer field. But have you ever stared into the center of a sunflower and really looked? Not just glanced, but looked, in the same way a curious child looks at a seashell for the very first time. If you have, you might have noticed something odd, or rather something oddly perfect. The seeds aren't scattered randomly, and they're not just crammed in as tightly as possible. They follow a pattern, a precise, swirling, mesmerizing pattern that mathematicians and nature lovers alike have come to recognize as one of nature's most elegant signatures, the Fibonacci sequence. Now don't worry, we're not going to dive into complex equations. This isn't math class and there won't be a quiz, but there is a fascinating little number story at the heart of this pattern. The Fibonacci sequence is a series of numbers where each number is the sum of the two numbers before it. It begins like this: 1, 1, 2, 3, 5, 8, 13, 21, 34, and so on. Simple enough. And yet, from that simplicity springs complexity and beauty that stretches across the natural world. Let's go back in time for just a moment. The man behind the name, Leonardo of Pisa, better known as Fibonacci, was an Italian mathematician who lived in the 12th and 13th centuries. He didn't invent the sequence. It had been used in Indian mathematics for centuries before him, but he did popularize it in Europe through his book, Liber Abaci, which sounds a bit like a magical spell, but was actually a practical manual for merchants. In this book, Fibonacci posed a curious question. How many pairs of rabbits will be produced in a year, beginning with a single pair, if every month each pair produces another pair which becomes productive from the second month on? Yes, rabbits. As it turns out, this fluffy hypothetical led to one of the most celebrated sequences in mathematics. The rabbit problem yields the Fibonacci sequence, and from there, things spiral outward, quite literally. Because those numbers don't just sit on a page. They seem to breathe within the structure of nature itself. In sunflowers, for example, the seeds are arranged in spirals that radiate outward from the center, and when you count them, clockwise and counterclockwise, you often find Fibonacci numbers. You might count 34 spirals in one direction and 55 in the other, or 55 and 89. The ratios remain wonderfully consistent. Why does nature do this? Is the sunflower secretly a mathematician? Well, not quite. The explanation is more grounded in physics and evolution. Plants want to pack seeds as efficiently as possible to make the most of the available space. Too much overlap and they waste valuable room. Too little and they don't use the space well. Enter the golden angle, which is derived from the golden ratio, a close cousin of the Fibonacci sequence. The golden angle is approximately 137.5 degrees. When seeds or petals grow at this angle from one another, they fill space incredibly efficiently without crowding. Imagine you're placing dots around a circle, and each new dot is placed 137.5 degrees around from the last. You end up with a spiral that seems to go on forever without repeating, and each new dot fits neatly into the gaps left by the ones before. That's what sunflowers do. That's what pine cones, pineapples, and even artichokes do too. They don't try to form spirals. The spirals are a side effect of following this deeply efficient growth rule. It's a little like a natural traffic system, where each new unit follows the same turn pattern and ends up in the optimal position. The result is order disguised as beauty, or perhaps beauty disguised as order. The golden ratio itself, often represented by the Greek letter phi, is about 1.618. It's an irrational number, which means it goes on forever without repeating, kind of like that one friend who never runs out of things to talk about at dinner. You can find this ratio in the spirals of galaxies, in the architecture of ancient temples, and in the proportions of the human body. Your arm, your fingers, even your face. Many of these follow approximate golden ratios. It's not a rule set in stone, but it does show up with suspicious frequency. Back in the natural world, spiral shells like the Nautilus are often cited as examples of the golden ratio, though this is a bit of a simplification. Many spiral shapes in nature are logarithmic spirals, which means they grow outward at a constant angle rather than a fixed curve. The golden spiral is a specific kind of logarithmic spiral, and while nature doesn't always hit it exactly, it gets close enough to make you raise an eyebrow. And here's a calming thought. This pattern-seeking behavior isn't just something humans impose on nature. It's something nature does on its own. Spirals, ratios, and sequences aren't decorations. They're tools. They're solutions. When a sunflower packs its seeds or a pine cone arranges its scales, it's doing so in the most efficient way possible, given the space, the nutrients, and the physics of its environment. These are not just pretty designs, they're mathematical adaptations. It's a reminder that beauty and function often go hand in hand. Nature is not just pretty for our benefit, it's efficient, it's optimized, and it just so happens that optimization often looks beautiful to us. Or perhaps we've evolved to find optimized patterns beautiful because they're so central to life and survival. You can see Fibonacci patterns in things as small as succulents and as large as hurricanes. Even spiral galaxies seem to echo these mathematical curves. The universe itself, in its spinning and stretching, seems to nod gently to the same numerical ideas that shape a flower. That might be coincidence, it might be emergent pattern, or it might be something deeper, some strange cosmic rhythm that binds the tiniest seed to the vastest star. Now, we could talk about the many places people think they see the golden ratio and Fibonacci sequence but actually don't. It's worth noting that not every spiral or pattern you see in nature is a direct result of Fibonacci. Sometimes we impose the pattern after the fact. It's a bit like seeing shapes in clouds. It's part of our human need to find structure. But even allowing for a bit of wishful thinking, there's no denying that the sequence does show up enough to be more than a coincidence. And yet, despite all this mathematical elegance, plants don't know math. They don't count. They don't solve equations. What they do is grow according to the rules of physics, chemistry, and biology. And those rules, it turns out, favour certain numbers and angles. The Fibonacci sequence is not the cause, but the result. A pattern that emerges naturally from simple rules applied over and over again, which, when you think about it, is rather reassuring. Nature doesn't need to be told what to do. It doesn't need instructions or blueprints. With the right conditions and enough time, order arises from simplicity. Spirals emerge. Seeds find their place. Everything moves outward in elegant, efficient loops. There's something deeply peaceful about that. In a world that often feels chaotic and rushed, the idea that a sunflower quietly follows a centuries-old sequence just to make the best use of space is a kind of quiet wisdom. It's nature's way of saying, slow down. Trust the pattern. Everything has its place, even the spirals. And as you settle deeper into rest, it's comforting to imagine that even in sleep, your body follows rhythms. Your breath, your heartbeat, the slow dance of your thoughts, all part of a greater pattern. One you don't need to control. One that's been unfolding since long before you were born, and one that, much like the spiral of a sunflower, carries on, quietly, beautifully, without ever needing to ask why. If you've ever held a fern in your hand and looked closely at the leaves, you might have noticed something curious. The fronds, the big leafy branches, are made up of smaller fronds. And those smaller fronds? They're made up of even smaller versions of themselves. It's a bit like nature took a single leaf, shrunk it, copied it a dozen times, and glued the pieces together into a larger version of the same thing. And then did it again, and again. This, in the world of mathematics and natural patterns, is what we call a fractal. A fractal is a shape or pattern that repeats itself at different scales. It's self-similar, meaning if you zoom in or zoom out, you still see something that looks roughly like the whole. In the case of the fern, each small leaf looks like a tiny fern of its own, nestled into the larger structure. In a coastline, you might see the same jagged curves whether you're looking at a few meters or a few kilometers, and if you've ever looked at a Romanesco broccoli, one of those bright green alien-looking vegetables with spiral towers, you've seen fractals on your dinner plate. What makes fractals so fascinating is that they live in the space between order and chaos. They're not completely regular, like a neat row of circles, but they're not completely random either. They have a kind of rough symmetry. You can recognize the pattern, but it doesn't repeat in the exact same way every time. Fractals are nature's way of being precise and messy at the same time. Now, mathematically speaking, fractals were given formal shape in the 20th century, but like many beautiful ideas, they existed in nature long before we knew what to call them. The term fractal was coined by the mathematician Benoit Mandelbrot in the 1970s. He was studying the question, how long is the coastline of Britain? A seemingly simple question, but the answer is surprisingly slippery. If you measure it with a long ruler, say 100 kilometers, you get a certain length. Use a shorter ruler, say 10 kilometers, and you measure more of the in and out curves, so the total length increases. Use a 1 meter stick, and suddenly you're picking up every tiny nook and cranny. The closer you look, the more coastline there is. The length, in a way, is infinite. This strange property, that the detail grows as you zoom in, is a hallmark of fractals. Mandelbrot took that idea and applied it to a wide range of patterns in nature, showing that many natural forms could be described using fractal geometry. Clouds, mountain ranges, blood vessels, tree branches, lightning bolts. All of them have this self-similar, irregular but patterned structure. Let's pause for a moment on clouds. Have you ever tried to draw one? It's not easy. A cartoon cloud is usually just a fluffy oval with some bumps. But real clouds have that complex textured edge, full of little curls and wisps that echo the larger shape. You can't really draw a cloud with a ruler and a compass. But fractal equations can approximate that kind of natural irregularity. They give you a tool for modelling the complexity of the real world. Things that are too messy for traditional geometry but too patterned to be considered random. And then there's lightning. A single bolt of lightning splits, then splits again and again in branching paths that look eerily similar no matter how far you zoom in. That jagged branching structure is a fractal too, and the same basic form shows up in river networks, the blood vessels in your body, and even in tree roots. It's a branching system that lets things move, electricity, water, blood, nutrients, through a space efficiently. Trees are particularly elegant examples. If you look at the branching of a tree, each large branch splits into smaller branches, and those into even smaller twigs. The angles, spacing and lengths may not be identical, but the structure echoes itself at every level. This allows trees to capture sunlight in a maximally efficient way, creating a vast surface area for photosynthesis without wasting space or energy. It's evolution sculpting geometry with a biological chisel. Fractals don't just show up in the visible structures of living things, they also show up in how those things function. Take your lungs. They're not just two big pink balloons. Inside, they branch again and again into smaller and smaller tubes, ending in millions of tiny sacs called alveoli. This branching system allows an enormous surface area to fit inside a relatively small space. It's estimated that your lungs, if flattened out, would cover an area roughly the size of a tennis court. All of that tucked neatly into your chest. A biological fractal at work. Even your heartbeat has fractal patterns. When your heart is healthy, the time between beats doesn't stay perfectly even. It varies slightly in a pattern that's complex and self-similar. Too regular, and it's a sign something's wrong. Too chaotic, and that's not good either. A healthy heart has a rhythm that's just irregular enough, dancing between order and disorder, much like the structure of a cloud or a coastline. Now let's talk about the Mandelbrot set. It's one of the most famous images in mathematics. A black blob with little swirls and curls around the edge, infinitely complex and beautiful. It's named after Benoit Mandelbrot, of course, and it's created using a very simple equation repeated over and over. The incredible thing about the Mandelbrot set is that if you zoom in, you keep seeing more detail. Not just tiny shapes, but entire landscapes of complexity. Spirals, lightning-like branches, shapes that echo the original form over and over again. It's like looking into a mirror made of math, where each layer hides another just waiting to be explored. And yet all of this comes from repetition. That's the magic of fractals. You start with a simple rule and repeat it, over and over, with just a few adjustments and a lot of iterations. Something astonishing begins to take shape. You don't need a complicated blueprint, you just need to follow the rule and let it unfold. This is how nature builds itself, not with grand plans, but with simple rules carried out many times. A tree doesn't know how to be a tree. It just grows a little stem, which branches. Those branches grow and branch again. The result is something that looks intentional, even artistic, but it's all driven by small steps, repeated with patience. There's a quiet lesson in that. In a world where we often feel the pressure to do big things quickly, fractals remind us that complexity can come from simplicity, that beauty can arise from repetition, that something as intricate as a fern or as sprawling as a thunderstorm can emerge from just doing the same thing, thoughtfully, again and again. And just as fractals exist in the physical world, they also sneak into the world of art and music. Some composers have used fractal algorithms to generate musical patterns. Visual artists have built entire landscapes and scenes from fractal structures. Even video games and digital animations rely on fractals to create lifelike environments. Rugged mountains, twisting trees, realistic coastlines, all born from fractal geometry. You might also notice fractals in cultural artifacts. Traditional African, Indian, and Islamic art sometimes includes fractal patterns in textiles, architecture, and decoration. Long before the word fractal was invented, humans had already been mimicking these repeating patterns in their craft. It seems our brains are drawn to them, even if we don't always realize it. What is it about these patterns that is so soothing? Maybe it's the way they suggest endlessness without chaos. They give you something to look at, to follow, without overwhelming you. They're structured but not rigid, predictable but not boring. Kind of like a forest trail that winds just enough to keep you curious, but not so much that you get lost. Fractals live in that in-between space, the edge of chaos, the edge of order. They're not one thing or another, they're both, balancing complexity and calm, and in their branching, spiraling, infinitely detailed forms, they invite you to look deeper, to slow down, to notice the way the world builds itself from the smallest pieces. And maybe, just maybe, to find a little comfort in the repeating rhythms of the universe. In the early 1960s, a meteorologist named Edward Lorenz was working on a rather humble problem, trying to predict the weather. He had built a simplified computer model of atmospheric conditions, a sort of stripped-down version of a weather system, with a handful of equations to represent temperature, pressure, and wind. One day, he ran the simulation, then wanted to repeat it from a midpoint to save time. But instead of typing in all the exact decimal numbers, he rounded them off slightly. Just a small change. Something like using 0.51 instead of 0.51372. He stepped away to get a cup of coffee, expecting the simulation to unfold nearly identically. But when he returned, the results had diverged completely. It was like he had created an entirely different weather pattern. His small rounding error had caused a massive change in the outcome. This seemingly minor hiccup led Lorenz to uncover one of the most profound ideas in modern science, chaos theory. And from that came one of the most famous metaphors in mathematics, the butterfly effect. In simple terms, it's the idea that a butterfly flapping its wings in Brazil might set off a tornado in Texas. Of course, that's not literally what happens, but the metaphor captures a deeper truth. In complex systems, small changes can lead to very big differences. Let's slow that down a bit. Chaos, in the scientific sense, doesn't mean randomness or disorder. It means deterministic systems, systems that follow rules, but whose outcomes are highly sensitive to initial conditions. You set things up the same way with just a tiny variation, and the whole trajectory changes. Like two balls rolling down a hill, if one starts just slightly to the left of the other, at first they look like they're taking the same path. But if the hill has bumps and curves and twists, those little differences grow over time until the balls are nowhere near each other. That's what Lorenz saw in his weather model. He didn't break the rules of physics, he followed them. But the results were unpredictable because the system itself was extremely sensitive. This realization was both exciting and a little alarming. It meant that, in theory, even with perfect equations, predicting long-term weather might be impossible. Not because the universe is random, but because it's just too complicated to track every butterfly wing. Chaos theory found its home in all sorts of natural systems. Weather is the classic example, but the same principles apply to ecosystems, planetary motion, population dynamics, and even the human brain. Anywhere you have a system with feedback loops, nonlinearity, and lots of interacting parts, chaos is just waiting around the corner, humming a quiet tune. Let's take a calmer example, dripping faucets. You might think a leaky tap is just annoying background noise, but researchers have studied the timing of water drips and found chaotic behaviour. At first, the drips are evenly spaced. Then they start to vary. Then the pattern becomes wildly unpredictable, even though the physics of the water, gravity and pressure haven't changed. What's happening is that the system moves from stability to chaos through something called bifurcation, where a small parameter change splits the system into new behaviours. One drip becomes two become four, and before you know it, you've got a symphony of chaos playing in your kitchen sink. Now imagine that on the scale of an ecosystem. A tiny change in temperature, rainfall, or species population can ripple outward and create entirely new balances, or imbalances. Chaos theory helps explain why ecosystems can suddenly collapse or transform, even if the change that triggered it was seemingly insignificant. A few too many fish caught in a lake, a few degrees warmer in the Arctic, and suddenly the dominoes start to fall. But chaos isn't always a harbinger of doom. It's also responsible for complexity. It's how simple rules can create rich, dynamic, and even beautiful patterns. Think of a flock of birds swirling in the sky. No one bird is in charge, and yet the group moves as if choreographed. This emergent behaviour is built on simple individual rules: maintain distance, align with neighbours, avoid collisions, and from that comes graceful, unpredictable motion. In mathematics, Chaotic systems often produce images known as strange attractors. These are visual representations of how a system behaves over time. They don't settle into a fixed point or loop endlessly. They spiral, loop, twist and fold into complex patterns that never quite repeat. The most famous of these is the Lorenz attractor, a set of swirly curves that look a bit like butterfly wings, which is oddly fitting. Even your heart rate and breathing patterns can show signs of chaos. Not random fluttering, but complex non-repeating variation that reflects the health and adaptability of your system. A completely regular heartbeat, like a metronome, might actually be a bad sign. The healthy human body thrives in the edge zone, stable but responsive, predictable but flexible. Let's wander for a moment into astronomy. The solar system looks orderly, with planets orbiting neatly like marbles on strings. But even here, chaos sneaks in. The gravitational interactions between planets create tiny nudges and pulls, and over millions of years these can lead to shifts in orbits. The motion of asteroids in particular can be wildly chaotic. Small changes in velocity or position can fling them across the solar system or send them plummeting into a planet. Thankfully, space is big and chaos takes its time. Then there's economics. Entire markets can be thrown into disarray by a minor policy change, a rumour, or even a tweet. Financial systems are chaotic in the mathematical sense, not because people are irrational, although that happens, but because there are too many variables interacting in non-linear ways. One investor sells, another panics, algorithms react, and suddenly the entire market tilts. If all of this sounds a little unsettling, here's the comforting part. Chaos isn't the enemy of calm. In fact, the two often coexist. There's a quiet elegance in watching how the world balances between them. You can't predict every twist, but you can understand the boundaries. You can't see the exact path, but you can recognize the pattern. In nature, chaos creates diversity. It prevents stagnation. It encourages adaptation. A perfectly ordered system would be brittle. A purely random one, unworkable. But chaotic systems dance between the two. Think of a river, always flowing, never quite the same, yet always following gravity's pull, or a campfire, flickering, leaping, changing shape every second, yet still warm and inviting. That's chaos in its softer form, not destruction, but dynamic beauty. Even in your daily life, you brush up against chaos more often than you might think. Ever lost your keys and found them somewhere utterly unexpected, even though you always put them in the same place? That tiny moment of deviation, when you were distracted or in a hurry, set off a chain of events that led to a mystery and a minor crisis. Small causes, big effects, a classic butterfly wing moment. And while chaos theory has a solid foundation in math and physics, it's also deeply philosophical. It invites humility. It reminds us that certainty is often an illusion, that control is limited, that small acts matter. You never know what subtle influence your presence might have in a room, in a day, or in a life. Of course, this doesn't mean we should live in fear of consequences we can't predict. Quite the opposite. It means we can take comfort in the unpredictability. The world is allowed to surprise us. Outcomes aren't fixed. There's room for spontaneity, change, and the unexpected turn. At the heart of chaos theory is a simple but profound truth. Even in systems governed by strict rules, long-term outcomes can be uncertain. But this isn't a flaw. It's a feature. It's what makes the world interesting, alive, and endlessly full of possibility. The butterfly effect isn't just a quirky metaphor. It's a gentle reminder that even the tiniest actions can echo through time and space, that somewhere, in some unfolding chain of events, a small gesture, a passing thought, a quiet choice, might be the start of something much bigger than you could ever imagine. And there's a certain peace in that. Imagine standing in the middle of a forest, not rushing through it, not checking your phone for reception, or worrying about where the nearest coffee shop might be, just standing, listening to the wind move softly through the leaves, watching the slow sway of branches and feeling, even if you don't consciously realize it, that there's something deeply harmonious about the shapes around you. Trees don't just grow, they arrange themselves, and quietly they follow geometry. Let's start with something simple but easily overlooked, the way a tree branches. You've probably noticed it before, even without thinking much about it. A trunk splits into a few thick limbs. Those limbs split into smaller branches, those into twigs, and each of those has a few leaves or needles at the ends. It looks natural, organic, unstructured maybe. But there's math humming gently beneath it all. Trees don't branch randomly. They follow certain rules that have evolved over millions of years to help them survive, thrive, and reach for the light. One of those rules involves branching angles. That is, the angle at which a new branch grows out from the parent branch. It turns out this angle isn't just a fluke, it's optimized. If the angle is too small, branches grow too close together and block each other's access to sunlight. If the angle is too wide, the branch might be too weak or inefficient in supporting the leaves. But somewhere in the middle, often around 38 to 45 degrees, there's a sweet spot, a balance between strength and exposure. This optimal angle allows each new branch to maximize its light capture while minimizing shade on its siblings. It's a little like being in a crowded theatre and finding the one seat that gives you the best view of the stage, without sitting directly in someone else's line of sight. That's just one part of the geometry at play. Another important concept is something called phyllotaxis. This is the arrangement of leaves on a stem or branch. In many plants and trees, the leaves are arranged in spirals, yes, those spirals again, around the stem at angles that allow them to get the most sunlight without casting shadows on each other. The golden angle comes up here too, that roughly 137.5 degree rotation between leaves. It allows for the most efficient packing of leaves, giving each one a clear shot at the sun. It's a quiet choreography, but it's precise. Sunlight is energy, and energy is everything to a tree. Every inch of growth, every cell of wood, every drop of sap is powered by light turned into sugar. So it makes sense that trees would evolve to be incredibly efficient at harvesting that light. The geometry of their branches and leaves is the result of evolutionary tinkering with energy economics. Even their height is a balancing act. Taller trees can outcompete others for light, but they also need to transport water all the way from their roots up to their canopy. That's no small feat, especially when you're, say, a coastal redwood standing over 300 feet tall. Water moves through xylem vessels, pulled upward by evaporation at the leaves and cohesion between water molecules. It's elegant, but not unlimited. Gravity, resistance, and physics eventually put a cap on how tall a tree can grow. There's even a theoretical maximum height for trees, somewhere around 430 feet, beyond which the physics of water transport just can't keep up. Now, let's look at the tree as a whole. Its overall shape, the trunk rising, the branches spreading, the roots anchoring, isn't just a consequence of random growth. It's a living solution to a mathematical puzzle. How do you get the most surface area exposed to light while using the least amount of material and staying structurally sound? The answer lies in branching patterns, and these are fractal in nature. The structure of a tree is self-similar across scales. A large branch resembles a smaller branch. A twig resembles the branching of a sapling. This fractal pattern isn't just beautiful, it's incredibly efficient. It allows the tree to cover more space, collect more light, and transport nutrients with minimal material costs. Fractals show up in trees because they're great at solving a specific problem, how to fill a space effectively. The branching pattern creates a network where everything is connected, yet spread out. This is especially important for root systems. Roots, like branches, branch in a fractal way, allowing the tree to explore a vast volume of soil with a relatively small amount of material. It's an underground mirror of the above-ground canopy, a twin pattern growing in the opposite direction, seeking water and nutrients just as the branches seek light. This type of structure isn't unique to trees. Blood vessels in animals, the bronchi in your lungs, even the dendrites in your brain, all follow similar fractal branching. The logic is the same: spread out, reach many places, and do it efficiently. Your lungs, for instance, branch about 23 times from your trachea down to the alveoli, creating a surface area of around 70 square meters packed into your chest. That's about the size of a badminton court, folded and tucked between your ribs. In your brain, neurons branch like tiny trees. Dendrites reach out like roots and branches, seeking signals from other neurons. The shape of these networks affects how you think, remember, and react. It's trees, all the way down, living math, shaping biology. There's something deeply poetic about that. Trees aren't just biological organisms, they're physical manifestations of mathematical principles. You can describe their shape with algorithms, simulate them with computer models, even recreate their patterns in sculpture, architecture, or digital art. And yet, no two trees are ever exactly alike. They follow the same rules, but the results vary with wind, soil, competition, and chance. It's like each tree is writing its own version of a familiar poem, using the same rhythm but different words. Even the way a tree grows over time follows a kind of logic. Young trees invest energy in height, racing upward to escape the shade of their neighbours. Once they reach a certain height, they begin to spread, thickening their trunks, strengthening their branches. If a branch is damaged or shaded, the tree will redirect its growth to other areas. It senses where light is most abundant and adjusts accordingly. This isn't conscious behaviour, of course, it's cellular signalling and growth hormones at work, but the result is remarkably adaptive. A tree will lean, twist, or even reshape itself entirely to find the best position for survival. This adaptability also shows up in forests as a whole. Trees compete for light, but they also coexist. In a dense forest, trees will grow taller and straighter, with fewer lower branches. In an open field, the same species might grow shorter and broader, with wide spreading limbs. The geometry responds to the environment. It listens. And while we often think of forests as still, slow places, they're actually dynamic systems. Trees communicate through chemical signals and underground fungal networks, exchanging nutrients and information. Older trees may support younger ones. Stressed trees may warn their neighbours. There's a whole hidden system pulsing quietly beneath the soil, sometimes called the wood wide web, that adds another layer of complexity to this already intricate geometry. But step back for a moment. Think not just of the tree's function, but its form, the way branches stretch skyward, the curve of a bough in winter, the lace of bare twigs against the sky. There's a reason people have drawn, painted, and studied trees for centuries. Their structure is captivating. It feels familiar and mysterious at the same time. They are quite literally living equations, solving for light, water, strength, and balance. And yet, for all their mathematical precision, they never seem cold or mechanical. Quite the opposite. There's a kind of calm in their order, a rhythm, a deep, slow breath. In the end, the geometry of trees isn't just about how they grow. It's about how they work, how they optimize, adapt, and endure, how they manage to be efficient without losing grace. Quiet forests, quietly calculated, not by conscious thought, but by the relentless, beautiful logic of nature. And all we have to do to appreciate it is slow down, look up, and let the branches do the talking. Let's begin by imagining something small, quiet, and perfectly curved. A seashell, still damp from the tide, sitting in your palm. Its surface is smooth, its colours soft and sun-faded. You turn it gently in your hand, and you notice the shape. Curving inward, curling like a frozen wave, tight at one end and slowly widening at the other. It's not a random curve. It's not even just a pretty one. That curve is mathematical. That curve is ancient. That curve is a logarithmic spiral. The logarithmic spiral, sometimes called the equiangular spiral, is a pattern that keeps turning while getting progressively farther from its centre. But it does so in such a smooth and steady way that it looks almost hypnotic. The key feature is that with every quarter turn the spiral grows by the same factor. Not by the same amount, but by the same ratio. That's the magic of it. The spiral expands, but it does so proportionally. It's like nature took a compass and drew a swirl, but the pencil moved farther away at just the right rate each time around. You'll see this spiral hiding in all sorts of shells, but the most iconic example is the nautilus. This beautiful marine creature, with its coiled shell and tentacled face, is something of a living fossil. It's been around for hundreds of millions of years, cruising through the oceans while dinosaurs stomped on land. The nautilus adds new chambers to its shell as it grows, each chamber larger than the last, maintaining that smooth spiral. It doesn't curl tighter and it doesn't flatten out. It holds that perfect curve, again and again, as if it's following some internal blueprint, a mathematical guide printed right into its DNA. But the nautilus isn't doing it to be stylish. The spiral is functional. Each new chamber the nautilus builds is part of a buoyancy system. The older chambers are sealed off and filled with gas, while the creature lives in the outermost one. By controlling the gas in the chambers, the nautilus adjusts its buoyancy, floating up or down in the water like a slow-moving submarine. The logarithmic spiral allows it to grow without changing shape. This means it can maintain its proportions as it ages, no redesign required. This kind of proportional growth is known as isometric growth, in contrast to, say, a baby bird that changes dramatically in shape as it matures. The nautilus stays the same, just scaled up. It's a clever strategy, and it's one that doesn't require reinventing the wheel with each birthday. Add a chamber, stick with the spiral, carry on. Other mollusks use similar logic. Many gastropods, like snails and whelks, grow their shells in spirals too. Even some ammonites, those extinct relatives of the nautilus, followed the same formula, despite having vanished from the Earth around 66 million years ago. Clearly, spirals are a pattern that works, and nature tends to keep what works. But shells aren't the only ones in on the spiral secret. Spirals show up in plenty of places where shells aren't involved at all. Take hurricanes, for instance. That swirling cloud mass you see from a satellite image isn't just dramatic weather. It's also a spiral shaped by the rotation of the Earth, the Coriolis effect, and pressure gradients in the atmosphere. The spiral arms of a hurricane form as warm, moist air rises at the centre, and the storm pulls in more air from the surroundings. The whole thing rotates, tightens, and stretches outward, creating that familiar whirl. And then there are spiral galaxies. Our own Milky Way, along with billions of others, curls through space in massive spirals. The stars don't spiral because of gravity alone. It's a more complex process involving something called density waves. In short, stars and gas move through regions of higher density, kind of like cars bunching up in traffic jams. As they do, they light up and slow down, giving the illusion of spiral arms. The arms are patterns, not fixed structures. But the result is the same, a galaxy that spins, curves, and stretches across light years in a graceful sweep. If that's not impressive enough, spiral patterns also show up inside your own body. Deep within your ear lies the cochlea, a spiral-shaped structure that helps you hear. This tiny organ is curled into a spiral to conserve space while maximizing surface area. Inside, it's filled with fluid and lined with thousands of tiny hair cells that respond to different frequencies of sound. High-pitched sounds are detected near the base of the spiral, lower pitches near the tip. The spiral shape isn't just decorative, it allows your ear to decode sound frequencies with remarkable precision. You could say your ear is a very quiet mathematician, unwinding music into its component parts. Even the way galaxies spin, hurricanes swirl, and cochlea curl, all of it seems to come back to one thing: the spiral as an efficient natural solution. Spirals are space-saving. They are growth-accommodating. They are, in a word, practical. And as is often the case in nature, what's practical becomes beautiful. Spirals also turn up in other living forms. Ram's horns curl into spirals. Spiderwebs often begin with a central spiral. Tendrils of climbing plants spiral as they search for support. The tails of seahorses and chameleons coil into neat curls. DNA itself, while a double helix rather than a flat spiral, still reflects the idea of twisting symmetry. The spiral form, in all its variations, seems to whisper something fundamental about the way energy, growth, and structure come together. There's something oddly comforting about that. Despite all the complexity in nature, despite the sheer variety of forms and colours and functions, certain shapes come back again and again. Spirals are one of them. Whether you're looking at a sunflower, a seashell, or a galaxy millions of light years away, the shape feels familiar, recognisable, reassuring, as if the universe keeps doodling the same curve in different notebooks. And while the Nautilus shell is often mistakenly thought to be a perfect golden spiral, a specific type of logarithmic spiral related to the golden ratio, it's usually only an approximation. The truth is, many natural spirals don't match the golden spiral exactly. Some are steeper, some are shallower. Nature isn't obsessed with mathematical purity. It's not trying to match a diagram in a textbook. It's using principles that are close enough. The logarithmic spiral is a general idea, a direction, a tendency, not a requirement. That's actually one of the more beautiful truths about natural math. Nature doesn't demand perfection, it rewards functionality. If a shell grows slightly off course but still works, that's fine. If a hurricane's spiral isn't textbook exact, the storm still spins. The spiral, like so many natural patterns, is flexible. It allows room for variation, adaptation, and evolution. It's also worth noting that spiral formation isn't always the result of conscious design, or even genetic instruction. Often it emerges from simple rules applied over time. In a growing shell, the rate at which material is added combined with the curvature of the shell's lip and the stiffness of the tissue can naturally produce a spiral. Nothing has to know the math. The math just unfolds as a consequence of growth. That, in a sense, is nature's great secret. Complexity from simplicity. A few rules, a few forces, time, and the spiral reveals itself again and again. You can even see this kind of emergent spiral in places like water, draining in a sink, or cream swirling in coffee. The way tornadoes twist, the way galaxies stretch, even the way your own hair might curl in a spiral at the crown of your head. It's all connected, not in a mystical sense, but in a structural one. Similar forces lead to similar outcomes. The spiral, then, isn't just a shape, it's a story, a record of how something has grown, stretched, or spun through space. When you hold a shell in your hand, you're not just holding an object, you're holding a timeline. The entire life of that creature, traced in calcium, winding outward in a precise and elegant arc. Every curve, every chamber, every swirl is a chapter. And if you find yourself walking along a beach, picking up shells and turning them over in your hands, maybe it's comforting to know that what you're holding isn't just pretty, it's patterned, ancient, familiar. A quiet echo of the same curves that shape storms, galaxies, and the hearing inside your head. A soft spiral, written over and over again in nature's notebook. There's something almost magical about snowflakes. They fall silently, gently, without fanfare. Yet if you catch one on your mitten and look closely before it melts, what you see is anything but ordinary. Each tiny flake is a six-sided work of art, symmetrical, intricate, and fleeting. It's hard to believe that something so small, made only of frozen water, could contain such delicate geometry. But there it is, 6 arms radiating outward like spokes on a wheel, each one mirroring the others with astonishing precision. It's nature's frozen blueprint, drifting down from the sky. What's even more remarkable is that snowflakes don't start out this way. Each begins as a tiny speck, maybe a dust particle or a bit of pollen, floating high in the atmosphere. Water vapour condenses around it, forming ice, and as the flake tumbles through the sky, the temperature and humidity around it change constantly. These subtle environmental shifts influence how the crystal grows, leading to the branching patterns we see. The six-fold symmetry comes from the molecular structure of water itself. Water molecules arrange themselves in a hexagonal lattice when they freeze, and that symmetry echoes outward as the flake grows. No two snowflakes are exactly alike, and yet all follow the same basic rules. The symmetry arises not from perfection, but from consistency. Every branch of a snowflake grows under nearly identical conditions, so they tend to mirror each other. It's a kind of spontaneous order, emerging from physics and chemistry. You don't need a designer, you just need water, cold air, and a bit of time. Now shift your gaze from snow to soap, specifically a soap bubble, a shimmering floating sphere that lasts only moments before bursting. Unlike snowflakes, which form through solid crystal growth, bubbles form because of surface tension, a force that pulls molecules at the surface of a liquid into the tightest possible shape. And what is that shape? A sphere. Always a sphere. This isn't just a coincidence. A sphere is the shape that encloses the most volume with the least surface area. Nature loves efficiency. When soap and water stretch out to form a bubble, surface tension pulls the film into a shape that minimizes energy, and the sphere wins every time. But bubbles don't stop at being pretty. They also reveal how geometry can emerge from physical forces. If you press two bubbles together, they flatten slightly at the point of contact, forming a shape that shares surface area. Three bubbles form angles of 120 degrees between their membranes. More bubbles create hexagonal patterns. It's all very polite and very mathematical, like the bubbles have an unspoken agreement to share space fairly. You can find similar patterns in things like honeycombs, where bees construct hexagonal cells because they use the least wax to hold the most honey. Again, it's geometry doing its quiet work, helping life build efficiently without wasting energy. Symmetry shows up everywhere in nature, and not just in snowflakes and bubbles. Flowers often have symmetrical petals, 3, 5, or 6 in a circle. Starfish have 5 arms arranged radially. Even the simplest of creatures like jellyfish display rotational symmetry. For many organisms, symmetry offers practical advantages. It helps with balance, movement, and even camouflage. A symmetrical body plan lets an animal move efficiently and stay oriented in its environment. In humans, symmetry is especially intriguing. Our bodies are built with bilateral symmetry. 2 arms, 2 legs, 2 eyes, 1 nose in the centre. Of course, we're not perfectly symmetrical. 1 foot might be slightly bigger than the other, and almost everyone has a dominant hand or a stronger eye. But the general layout holds. A mirror split down the middle. Why? One big reason is that it simplifies development. Our DNA doesn't have to write separate instructions for each side. It can use the same blueprint and flip it. It also helps with locomotion. Walking, running, swimming. They're all easier when your left side and right side can coordinate smoothly. But symmetry in humans isn't just physical. It's psychological too. Studies have shown that people tend to find symmetrical faces more attractive, not because we're shallow, but because our brains are wired to process symmetry quickly. It's easier to recognize, easier to remember, and often, though not always, correlated with good health during development. We see symmetry as a sign of stability, a kind of visual trustworthiness. This might explain why symmetry appears so often in art, design, and architecture. From ancient temples to modern logos, symmetrical patterns create a sense of balance and harmony. They're pleasing to the eye, soothing to the brain. There's a reason mandalas, those intricate circular designs used in many cultures for meditation, are symmetrical. Their repetitive mirrored patterns invite focus, calm, and contemplation. But nature doesn't limit itself to one kind of symmetry. There's radial symmetry, like in sea urchins and flowers. There's bilateral symmetry, like in animals. There's even spiral symmetry, as seen in shells and galaxies. And sometimes, symmetry breaks. Think of a crab with one claw larger than the other, or a tree growing at an angle because of the wind. These asymmetries aren't flaws, they're adaptations. In biology, function always takes priority over form. If breaking symmetry offers an advantage, evolution is more than happy to do so. Even within the human brain, symmetry and asymmetry coexist. The left and right hemispheres are physically similar but functionally distinct. Language tends to reside in the left hemisphere for most people, while spatial reasoning leans toward the right. The symmetry provides structure. The asymmetry provides specialization. It's a partnership more than a competition. There's also something deeply human about our fascination with symmetry. We find it in snowflakes and bubbles, in faces and flowers, in the slow unfolding of petals and the perfect circle of the moon. We replicate it in everything from architecture to embroidery. And yet, we also recognize the value of asymmetry. A jazz solo that veers unexpectedly, a painting with an off-center subject, a story with a surprising twist. Too much symmetry can feel rigid, too little, and things become chaotic. The sweet spot lies somewhere in between. Just enough order to feel stable, just enough variation to stay interesting. This balance is perhaps why natural symmetry feels so satisfying. It never tries too hard. A snowflake doesn't strive to be perfect. It just is, following the laws of physics, forming quietly as it falls. A bubble doesn't plot its spherical shape. It's simply the result of tension and air. The patterns aren't forced. They emerge. And yet, we can't help but admire them, photograph them, study them, try to recreate them. There's a childlike wonder in discovering symmetry in a place you didn't expect. The six-pointed star on a snowflake, the repeating curve in a leaf, the mirrored pattern in a dragonfly's wings. Symmetry speaks to something deep in us, perhaps the part that craves order in a disordered world, the part that seeks meaning in patterns. Or maybe it's just that, in a universe full of noise, symmetry offers a quiet kind of music, a harmony we can see. And in those soft, silent moments, a snowflake caught on your glove, a bubble drifting in the sunlight, a perfectly balanced flower blooming in a patch of grass, you glimpse the gentle geometry at the heart of everything, the stillness within complexity, the simplicity within the swirl. You don't need to understand the math to feel it. It's already there, woven into the world around you, balanced, mirrored, waiting quietly to be noticed. If you've ever stared at a map and traced your finger along the outline of a country, maybe the winding edge of a coastline or the jagged lines of a mountain range, you might have had the curious sensation that the closer you look, the more there is. It's like chasing the edge of a puzzle piece that keeps adding new curves and corners every time you squint harder. That feeling isn't just in your head. It turns out there's real math behind it. Welcome to the world where geography meets geometry, and where terrain becomes a tangled web of patterns and complexity. Let's start with something deceptively simple. Measuring the coastline of Britain. You'd think this would be straightforward. Just find a good map, grab a ruler and start tracing. But here's where things get tricky. If you use a long ruler, say 100 kilometers, you'll get a certain measurement. Use a shorter ruler, maybe 10 kilometers, and you'll notice more detail. Every bay, every inlet, every small bulge or dip, and your total length increases. Use a 1 kilometer ruler and it increases again. As your ruler gets smaller, your measurement gets longer. Keep zooming in, and you'll find more crinkles, more edges, more length. This puzzle is famously known as the coastline paradox, and it was popularized by mathematician Benoit Mandelbrot in the 20th century. It challenges the very idea of measuring something that appears so concrete. Unlike a straight line, a coastline doesn't have a definite length. It depends entirely on the scale at which you measure it. The more detail you capture, the more complicated the line becomes. The reason this happens is because coastlines are fractal. That is, their patterns repeat at different scales. If you look at a large section of coast, you'll see bays and peninsulas. Zoom in, and you find smaller coves and rock outcroppings. Zoom in further, and even the rocks have jagged edges, worn by waves into miniature cliffs and folds. The structure continues, from kilometers down to meters, even down to grains of sand if you really push it. Each level adds more detail, more length. There's no smooth line to follow, just more and more complexity. Fractals, as you might remember, are patterns that repeat at different scales. Coastlines are a perfect example in the natural world. They're shaped by countless forces: waves, tides, erosion, tectonics, and they reflect that history in their endlessly wrinkled edges. The result is a boundary that isn't straight, isn't circular, isn't even neatly curvy. It's messy, but with a kind of organised messiness. A mathematical fingerprint etched into geography. Now shift your gaze inland, away from the coast and toward the veins of the land, rivers. From the sky, rivers look like networks of branching threads. A main channel meanders through valleys, fed by smaller tributaries, which are in turn fed by even smaller streams. The structure is unmistakably fractal. Each level of the network resembles the next, smaller and smaller forks feeding into one another. This isn't just a coincidence. It's the result of physics, gravity and erosion working together over time. Rivers carve their paths in response to the land's slope, the type of soil or rock, and the amount of water moving through. As water flows downhill, it erodes the ground, carving channels that deepen and widen over time. The branching pattern emerges naturally as the system tries to move water as efficiently as possible. Smaller tributaries carry runoff from local rainfall. Larger ones collect that water and funnel it downstream. The shape is dictated by the terrain, but the pattern is astonishingly consistent. In fact, river networks follow laws. Not laws written by humans, but statistical relationships known as scaling laws. One of them, called Hack's law, describes how the length of a river relates to the area of its drainage basin. It turns out you can make predictions about the shape of river systems just by understanding their mathematical properties. The complexity, while real, is not chaotic. It's ordered in disguise. This same order emerges in the way rivers meander. If you've ever flown over a landscape and seen a river that winds back and forth in lazy curves, you've witnessed another kind of pattern. Rivers don't always follow straight paths. Instead, they erode their banks unevenly, carving out bends that grow and shift over time. These meanders follow predictable rules too. There's even a relationship between the length of a river's meanders and the width of its channel. It's almost eerie, like the river knows how much it should twist and turn. Erosion also sculpts mountains, and while mountains may appear chaotic, a jumble of peaks and cliffs and ridges, they too follow patterns. If you look closely at the outline of a mountain range, it shares that fractal quality, jagged at every scale. The ridges split into smaller ridges, which split into gullies, which split again into smaller features. The process that creates these features, tectonic uplift combined with erosion, plays out over vast timescales, but the resulting geometry is quietly consistent. Interestingly, scientists can model these landscapes using relatively simple rules. One method, called diffusion-limited aggregation, simulates how particles build up over time. By letting virtual particles fall and stick wherever they touch a surface, researchers can create digital landscapes that look surprisingly like real ones. The complexity arises not from a complicated algorithm, but from a simple process repeated many times. This is a common theme in nature, complexity from simplicity. The most intricate patterns, the branching of rivers, the craggy face of a cliff, the outline of a coastline, don't require elaborate planning. They emerge from basic rules interacting over time. Add water, add gravity, add time. The math reveals itself. Even the distribution of mountain heights follows a statistical pattern. If you plot the number of peaks against their elevation in a given range, you often get a predictable distribution. In many cases, this fits a fractal dimension, a measure of how rough or detailed a surface is at different scales. It turns out you can assign a numerical value to how craggy a mountain range is. A lower fractal dimension means it's smoother, more rolling. A higher one means it's rough, rugged, deeply carved. This might sound abstract, but it has practical uses. Understanding the fractal properties of terrain helps with everything from flood prediction to satellite imaging. Engineers use these principles to simulate landscapes in video games and movies. Environmental scientists use them to understand how water moves through soil and rock. Even military planning takes terrain complexity into account. The math of the land matters more than we often realise, and while we tend to think of landscapes as fixed, they're actually in constant motion, just too slow for us to notice. Mountains rise, rivers shift course, coastlines creep inland or out to sea. Over decades, centuries, millennia, the land reshapes itself, all according to laws we can model and sometimes even predict. The Earth writes in slow handwriting, but the equations are there if you know how to read them. There's a kind of quiet satisfaction in knowing that the messy outline of a cliff face, or the erratic bend in a river, isn't random. It's the result of processes that are logical, repeatable, and deeply beautiful. The curves of a stream, the folds of a valley, the harsh spines of a mountain, all of them shaped by water flowing downward, rock resisting then yielding, and time pushing steadily forward. And perhaps most remarkable of all is that we can understand this. With our limited brains and short lifespans, we can trace the fingerprints of the planet's vast sculpting hands. We can model, measure and map what at first glance seems too complex to grasp. We can look at a river and see not just water, but pattern. Not just erosion, but structure. Not just geography, but geometry. So the next time you find yourself gazing out at a landscape, whether it's a windswept coast, a winding stream, or a distant mountain, know that hidden in its forms is a quiet math. A story told in curves, angles, and repeating lines. A story written not with ink, but with gravity, water, and stone. And once you start to see it, you'll find it everywhere. In every ripple, every ridge, every line drawn by the Earth's patient hand. You've probably seen it before, maybe while looking up at the sky on a quiet evening. A flock of birds, hundreds of them, swooping and swirling together in the air, forming shapes that shift and ripple like silk in the wind. There's no leader barking instructions, no flashing lights to guide them, yet somehow they move as one. They twist, turn, dive, and rise, all without colliding. It's mesmerizing, almost hypnotic, and strangely mathematical. This type of coordinated group behavior, whether in birds, fish, insects, or even people at times, is called emergent behavior. It's what happens when individuals follow simple rules, but those simple rules give rise to complex group dynamics. No one bird is in charge, and no single fish dictates direction. Each member just pays attention to a few neighbours, and the pattern unfolds naturally. Take starlings, for instance. When they form those breathtaking clouds in the sky, known as murmurations, they're each responding to the position and movement of about 6 or 7 nearby birds. That's it. They don't have to track the whole flock. By aligning themselves, keeping a bit of space, and adjusting their speed based on their closest neighbours, they collectively create a dance in the sky. Fish do something similar. Schools of fish move in tight formation, shifting direction almost instantly when threatened, or turning in perfect arcs as if choreographed. Each fish is reacting not to the group as a whole, but to the fish directly beside it. If one fish turns, the next responds, and the change cascades outward like a ripple on a pond. It's fast, efficient, and incredibly hard to disrupt. Try catching a fish in the middle of a school and you'll understand just how well that system works. This isn't telepathy, it's not even conscious thought necessarily, it's just rules, simple, local rules. Keep close but not too close, move in the same direction, adjust your speed, and suddenly, without anyone giving orders, the group becomes a living system, flowing through space as if it had a mind of its own. You might wonder how these animals process all this information so quickly. After all, avoiding collisions, keeping formation, and responding to danger requires constant vigilance. But nature, as usual, has streamlined things. Birds and fish don't calculate trajectories like little flying or swimming computers. Instead, their nervous systems are wired for quick instinctual responses. Visual cues, subtle shifts in pressure, and the behavior of their neighbors guide them in real time. It's less thinking, more reacting. Computer scientists and mathematicians have studied this kind of behavior for decades, and they've even used it to design algorithms. There's something called the Boyd's model, developed by Craig Reynolds in the 1980s, which simulates flocking behavior using only 3 simple rules: separation, alignment, and cohesion. When applied to virtual agents, these rules produce behavior that looks uncannily like real bird flocks or fish schools. No master plan, just local decisions leading to global patterns. Now zoom in a bit, close to the ground, and you'll find another example of organized chaos. Ants. Ant colonies are tiny factories of efficiency, buzzing with activity, yet seemingly directionless. Still, if you watch closely, there's a method to their movement. Ants lay down pheromone trails as they explore. If one finds food, it heads back to the nest, laying down a stronger trail. Other ants follow that trail, reinforcing it as they walk. Over time, the most efficient path to the food source becomes the most heavily used, simply because it's the most reinforced. It's a decentralized decision-making system, driven by feedback and chemistry. What's fascinating is that this process can solve complex problems. In fact, engineers and computer scientists have borrowed the ant trail idea to develop optimization algorithms. These so-called ant colony optimization models are used to figure out the best routes for delivery trucks, the most efficient layout for networks, or even how to schedule tasks in complicated systems. Tiny insects just following scent trails helped inspire tools that optimize modern logistics. And it's not just ants. Bees communicate using dances, literal wiggly dances to tell each other where to find nectar. Termites build towering mounds with intricate ventilation systems, all without a blueprint. Fireflies in some regions flash in perfect unison, thousands of lights blinking in harmony. These are all examples of emergent behavior, where small, simple actions create something that looks remarkably like planning, even though it isn't. One of the most compelling things about these systems is their resilience, because there's no central controller, there's no single point of failure. If a few birds fly off, the rest of the flock keeps moving. If a few ants get lost, the colony still functions. The system adapts in real time. This robustness is something engineers strive to replicate in technology, especially in areas like robotics and artificial intelligence. If you've ever seen a drone swarm, small flying robots moving together like a flock of birds, you've seen this principle in action. Each drone follows simple rules, using sensors and algorithms inspired by fish and birds, and the result is a coordinated, graceful ballet of machines. It's elegant, efficient, and very much borrowed from the animal kingdom. What makes all of this even more remarkable is how calming it can be to observe. Watching a murmuration of starlings, a school of fish gliding through water, or even a slow stream of ants moving along a path has a strangely meditative quality. It feels both chaotic and organized, full of motion but not rushed. There's a rhythm to it, a flow that's hard to describe but easy to feel. Part of the appeal might be that these systems reflect something we're always looking for: connection without hierarchy, movement without command, order without control. There's something comforting about seeing hundreds of individuals moving as one, responding to each other, adapting, and creating beauty without needing to explain how. And this principle doesn't just apply to animals. Humans exhibit emergent behavior too, whether we realize it or not. Think of pedestrians weaving through a crowded street, avoiding collisions without speaking, or people dancing in a crowd, adjusting their movement to match the energy around them. Even traffic, for all its frustrations, is a kind of large-scale emergent system. When it works, it feels seamless. When it breaks down, well, it reminds us that not all systems are perfectly tuned. Still, when humans coordinate well, the result can be astonishing. Consider a well-practiced marching band, a team of rowers moving in perfect unison, or a flash mob that erupts in synchronized dance. These displays are often pre-planned, yes, but they tap into the same principle: simple rules, shared cues, local adjustments, and a shared rhythm. At its heart, the beauty of these behaviors lies in their simplicity. You don't need a brain the size of a watermelon to move in harmony. You just need a few instincts, a few signals, and an openness to feedback. Nature has figured this out in countless ways, and in doing so, it's created systems that are not only efficient but also breathtaking. Perhaps there's a quiet lesson in this, that sometimes the most graceful solutions don't come from top-down control but from gentle coordination, that we don't always need to be in charge to be part of something beautiful. That connection, awareness, and response can create patterns far larger and more intricate than any single mind could design. So the next time you see a flock in the sky or a trail of ants marching purposefully along a sidewalk, pause for a moment. You're not just watching animals go about their day, you're witnessing one of nature's most elegant tricks, turning the simple into the spectacular, the local into the global, and the ordinary into something quietly extraordinary. You might not picture a bumblebee holding a calculator or a sunflower solving equations, but nature has a sneaky way of doing math without ever writing anything down. Animals and plants don't do math the way humans do, of course. There are no blackboards in bird nests and no spreadsheets in the soil, but that doesn't mean they're not using numerical strategies. In fact, a surprising number of species show evidence of what we might call number sense, a natural ability to recognize patterns, optimize behavior, and solve spatial puzzles that would make even a seasoned mathematician raise an eyebrow. Let's start with one of the most mathematically gifted members of the insect world, the honeybee. Bees don't just fly around aimlessly sniffing flowers. Their lives are structured, efficient, and astonishingly geometric. And nowhere is that more beautifully apparent than in the honeycomb. Each honeycomb cell is a perfect hexagon, 6 sides of equal length, packed together in a repeating pattern. Hexagons are not the easiest shape to build, so why do bees use them? The answer, as it turns out, is efficiency. Of all the shapes that can fill a flat surface without leaving gaps, triangles, squares, and hexagons, the hexagon requires the least amount of wax to hold the most honey. It's the best way to build a strong, storage-friendly structure with minimal material. It's math, baked right into the biology. What's even more impressive is that bees can understand relative quantities. Studies have shown that bees can distinguish between different numbers of shapes. For example, choosing a flower that has 3 dots instead of 4 to earn a reward. They don't count like we do, but they can estimate, compare, and even understand concepts like more or less. In one experiment, bees were trained to associate a certain number of objects with a sugary treat. They learned to recognize quantities and even apply simple rules like choose the group with fewer items. For a creature with a brain smaller than a sesame seed, that's not bad at all. Now take to the skies and consider birds. Migratory birds, like the Arctic tern or the bar-tailed godwit, travel thousands of kilometers across oceans and continents, often returning to the same nesting grounds year after year. How do they do it? They're not following road signs or checking GPS. Instead, they use celestial geometry, an internal compass guided by the stars, the sun, and the Earth's magnetic field. Birds can detect the angle of the sun relative to the horizon, and many use the stars as a navigational map. Some species, like the indigo bunting, have been shown to orient themselves based on the position of constellations, particularly the North Star. In laboratory settings, young birds raised under planetarium skies learn to navigate by star patterns, even if they've never seen the real night sky. It's not just memory, it's spatial awareness tied to the natural geometry of the heavens. What's more, birds use visual landmarks, patterns in the landscape, and even polarized light to fine-tune their routes. The fact that they integrate so many sources of information, celestial, magnetic, topographic, suggests a kind of internal trigonometry. They are in essence solving a multivariable navigation problem with their brains, recalibrating in real time as they travel. It's not the conscious math of humans, but it's no less extraordinary. Birds also display numerical abilities in social situations. Crows, ravens, and parrots in particular have shown the ability to count small numbers, solve puzzles involving sequences, and even anticipate future outcomes. Crows have been observed placing objects in order of size, dropping stones into water to raise the level and retrieve floating food, and recognizing the difference between different quantities in foraging scenarios. Some researchers believe they understand the concept of zero, something that took humans a remarkably long time to figure out. Even chickadees, those tiny round songbirds often seen flitting through snowy branches, organize their memories by spatial layout. They cache seeds in hundreds of locations and remember where they put them, sometimes for months. This kind of memory is deeply tied to spatial reasoning and may involve mental mapping that mirrors geometric logic. It's practical, survival-driven math. While we're underground in thought, let's turn to something even more unexpected: plants. At first glance, plants seem like the last place you would expect to find number sense. They don't have brains, they don't move quickly, and they certainly don't take math exams. But plants are problem solvers in their own slow, quiet way. Their roots grow in search of water and nutrients, and this growth isn't random, it's optimized. Root systems follow branching patterns that are fractal in nature. They split and split again, covering ground in a way that maximizes absorption while minimizing energy expenditure. Each root tip can respond to local conditions, moisture, soil density, chemical signals, and adjust its growth direction accordingly. The overall result is a structure that appears planned, even though no single part of the plant is doing the planning. There's a particularly elegant example of this in climbing plants. Some vines spiral upward in search of support, tracing helical paths that follow the sun's movement across the sky. This behavior, known as circumnutation, involves a constant adjustment of growth direction to maximize exposure to light. It's geometry in motion, slow motion to be sure, but no less precise. Some research suggests that plant roots can solve simple mazes in laboratory experiments. When placed in a forked pathway, with one branch leading to nutrients and the other leading to nothing, roots will preferentially grow toward the reward. They do this by detecting gradients in chemical signals and choosing the optimal path. It's not reasoning in the human sense, but it is decision-making based on environmental input and spatial logic. Sunflowers also show geometric precision. As they grow, their seeds arrange themselves in spiral patterns that follow the Fibonacci sequence. This packing method allows for the most efficient use of space and sunlight. It's not that the sunflower is calculating Fibonacci numbers, it's that the genetic instructions guiding its growth naturally produce that arrangement. It's emergent geometry, encoded in biology. And then there's slime mold. Technically not an animal or a plant, this strange amoeba-like organism has demonstrated problem-solving skills that seem oddly intelligent. In one famous experiment, researchers placed food sources on a petri dish in the same layout as major cities surrounding Tokyo. The slime mold grew a network of nutrient-carrying tubes that mirrored the layout of the actual Tokyo subway system. Efficient, minimal, and well-connected. No central brain, no planning committee, just local rules producing a global solution. All of this raises an intriguing question. Where does math really begin? Is it only something humans do when we count on our fingers or scribble equations on paper? Or is it more universal, something built into the way organisms navigate, survive, and grow? It seems increasingly clear that nature does math in its own quiet way. Not through symbols or formulas, but through shapes, patterns, and behaviors that align with mathematical principles. Hexagons in hives, spirals in seeds, networks in roots. Optimization, estimation, measurement, orientation. These aren't just human inventions. They're strategies life has evolved over millions of years. Even the way animals forage often follows mathematical principles. In a search pattern known as Levy flight, many animals alternate between short movements and occasional long jumps. This type of motion has been shown to be an efficient strategy when resources are scattered unpredictably. It's a strategy that balances thorough searching with wide coverage. Again, not consciously calculated, but incredibly effective. You don't need equations to find order in the natural world. The numbers are there, humming quietly in the background, guiding bees as they build, birds as they migrate, and roots as they dig. Nature may not be doing math in the way we understand it, but it's using the same principles to solve the same kinds of problems: how to move, how to find, how to build, how to grow. So whether it's a beehive, a bird's migration route, or a humble plant's root system, patterns are always emerging. They don't need blackboards or professors or calculators. They just need a purpose, a push, and time. And the math, like everything else in nature, unfolds with quiet precision. The world is full of rhythms, not just music, not just the ticking of a clock or the tapping of your fingers on a table. Real, deep rhythms that govern how living things grow, move, rest, and wake. You might not feel it while sitting under fluorescent lights or scrolling through your phone at midnight, but your body is quietly ticking to a natural rhythm, a schedule millions of years in the making, and it's not just you. From trees dropping their leaves to turtles laying their eggs, nature runs on clocks, not the mechanical kind, but biological ones. Let's start with the most familiar rhythm, the circadian cycle. It comes from the Latin circa diem, meaning about a day. Nearly every living thing on Earth has a circadian rhythm, a roughly 24-hour cycle that helps regulate when to eat, sleep, move, and metabolize. This internal clock isn't just a helpful suggestion, it's built into your cells. Deep in your brain, in a cluster of neurons called the suprachiasmatic nucleus, or SCN for short, your master clock keeps time using oscillating levels of hormones and gene activity. These rhythms aren't just tied to habits, they're tied to light. When sunlight enters your eyes, it signals your SCN to reset the clock for the day. That's why getting sunlight in the morning helps you wake up, and staring at a bright screen late at night can delay your sleep. Melatonin, the hormone that makes you feel sleepy, rises in the evening and falls in the morning. Cortisol, which helps with alertness, does the opposite. These hormone waves gently guide your energy levels, your mood, even your digestion. And this isn't just a human feature. Fruit flies, mice, fish, plants, even single-celled organisms show daily cycles. Flowers open and close in response to light. Fungi release spores at specific times of day. Coral reefs spawn in coordinated bursts synchronized by moonlight. The biological clock is one of the most ancient and universal features of life on Earth. It makes sense, really. Our planet spins, creating a cycle of light and darkness. Organisms that learned to align with this cycle had an advantage. Those that anticipated day and night could prepare, conserve energy, and stay safer. Over millions of years, this led to internal rhythms that match the Earth's rotation almost perfectly. It's a kind of math made of molecules and neurons ticking away without a watch in sight. Now zoom out a bit. Beyond the daily rhythm lies a grander, slower pattern, the seasons. Winter, spring, summer, fall, an elegant four-part harmony created by Earth's orbit around the Sun. But it's not just the orbit, it's the tilt. Earth leans at about 23.5 degrees, and as it circles the Sun over the course of 365.25 days, different parts of the planet receive varying amounts of sunlight. When the northern hemisphere tilts toward the Sun, we get summer. When it tilts away, we get winter. The southern hemisphere experiences the opposite at the same time. It's a beautiful geometric dance, written in orbital mechanics. The Sun's path across the sky changes slightly each day. The length of daylight shifts, temperatures follow, plants bloom, migrate, and sleep according to these shifts. Animals breed, migrate, hibernate. all in time with the Earth's orbit. The seasons are not just about weather, they are the background music to life's choreography. Farmers have known this for thousands of years, so have birds, insects and trees. Migratory birds time their journeys to the shifting seasons. Deciduous trees drop their leaves as daylight wanes and prepare for dormancy. Even microbes in the soil respond to temperature and moisture cycles. Everyone is listening to the same slow rhythm, even if we sometimes forget to hear it ourselves. Then there's the moon, a subtler drummer in nature's orchestra. The moon doesn't just light up the night sky, it tugs gently on the earth with its gravity, pulling at oceans to create tides. These tides rise and fall with a rhythm that's regular, predictable and deeply mathematical. The moon orbits Earth every 27 1/3 days, but because Earth is also moving around the sun, the cycle of moon phases, new moon to full moon and back, takes about 29.5 days. This lunar rhythm affects more than just the tides. Many animals time their behaviours to the moon's cycle. Sea turtles come ashore to lay eggs during certain phases of the moon, often around the full moon when the tides are highest. Coral reefs synchronise mass spawning events with the lunar calendar, releasing clouds of eggs and sperm on a schedule so precise it's like a biological festival of math. Some species of fish coordinate their activity with moonlight, becoming more active or more cautious depending on the brightness of the night. Insects, too, respond to lunar cues. Even human behaviour has been loosely linked to lunar phases, though the evidence is mixed. Sleep, mood, and even birth rates have all been studied in connection to moon cycles. Whether or not the full moon truly makes people act strangely, there's no denying that our history with it runs deep. But patterns in time aren't just about celestial mechanics. They also show up in the smaller rhythms of daily life, like naps. Yes, even naps are mathematical in their own way. The timing and length of a nap can dramatically affect how rested you feel. A short nap, around 20 minutes, taps into lighter stages of sleep, offering a quick energy boost without the grogginess that can come from waking in deep sleep. A nap that lasts about 90 minutes is a full sleep cycle, including light sleep, deep sleep, and REM. It's long enough to allow your brain to go through a complete circuit, improving memory and creativity. Anything in between, 30 to 60 minutes, can leave you feeling disoriented, as your brain gets pulled out of deeper stages without finishing the cycle. Sleep cycles themselves are rhythmic, lasting roughly 90 minutes each. You move through light sleep, deep sleep, and REM in waves throughout the night. That's why waking up at the wrong point in a cycle can feel jarring, while waking at the end of a cycle feels more natural. Some sleep tracking apps even try to time your alarm based on these rhythms to help you wake more gently. Your body temperature, blood pressure, and alertness also rise and fall throughout the day in predictable waves. There's often a natural energy dip in the early afternoon, a post-lunch lull when your internal clock signals a rest period. In cultures where siestas are the norm, people lean into this rhythm. In others, we power through it with coffee and fluorescent lighting. But the rhythm is there. Whether we acknowledge it or not, even our appetite follows patterns. Hormones like ghrelin and leptin rise and fall on a circadian schedule, affecting when we feel hungry and when we feel full. Digestion slows at night, which is why late-night meals can feel heavier. Our bodies are tuned to rhythms from the molecular level up to the planetary. In plants, these rhythms show up too. Many flowers open their petals at dawn and close them at dusk, tracking the sun even on cloudy days. This behaviour, known as heliotropism, allows plants to maximise their exposure to light. Some even anticipate sunrise, beginning to open just before the light returns. The math of their timing isn't conscious, of course. It's driven by internal signals and gene expression, but it's precise nonetheless. All of these rhythms, daily, monthly, seasonal, layer on top of each other, creating a kind of biological calendar that every living thing follows. Whether it's a hamster adjusting its activity to longer daylight hours or a sunflower turning slowly toward the sun, the timing of life is governed by math that most of us never see. But even if we're not conscious of it, our bodies are keeping score. They know what time it is, even without a clock. They anticipate light, prepare for darkness, and adjust to the pull of the moon and the tilt of the earth. It's a quiet symphony, and we're all part of it, yawning in unison, waking with the sun, drifting into sleep as the world darkens. There's something comforting in that, isn't there? In knowing that your body is part of a larger rhythm. That while your schedule might be full of meetings, traffic and alarms, underneath it all, a deeper pattern is ticking along, a pattern shaped by orbits, sunlight, and ancient evolutionary tuning. A pattern that whispers when it's time to rise, when it's time to eat, and when it's time to rest. And when you do finally rest, whether in a full night's sleep or a well-timed afternoon nap, you're not just recharging, you're aligning. Matching your internal metronome to the rhythm of the earth, letting the math of time carry you gently forward, one perfect cycle at a time. Close your eyes and listen for a moment, not just to the loud, obvious sounds, the traffic or the chatter or the hum of a refrigerator, but to the quieter, subtler rhythms underneath. A bird's call drifting through an open window, the hush of leaves moving in the wind, the distant roll of waves on a shore. These sounds are not just pleasant, they are patterns, vibrations, equations hidden in air. Sound is what happens when something moves and causes the air around it to ripple. Those ripples, or sound waves, travel to your ears and get translated by your brain into a symphony of meaning. Whether it's music, conversation, or the croak of a frog, all of it is made of waves, tiny compressions and rarefactions of molecules that dance through the air with astonishing precision. These waves follow rules, mathematical rules. The speed at which they travel depends on the medium. Sound moves faster in water than in air, and even faster in solids. The pitch, or frequency of a sound, is determined by how fast the wave is oscillating. High-pitched sounds have high frequencies, more wave peaks per second. Low-pitched sounds have low frequencies, longer, slower waves. An amplitude, the height of the wave, controls volume. Bigger waves mean louder sound. When you pluck a guitar string, strike a drum, or whistle a tune, you're creating vibrations that set molecules in motion. If those vibrations are steady and repeating, we call the result a tone. If they're chaotic and irregular, we get noise. But even noise in nature has its own flavour of order. Consider harmonics. When a musical instrument plays a note, it doesn't just vibrate at one frequency. It vibrates at multiple frequencies at the same time, called overtones or harmonics. These frequencies are whole number multiples of the fundamental note. Strike a middle C on a piano and you're not just hearing that single note. You're hearing its harmonics layered on top, giving it warmth and character. A pure tone, like one from a tuning fork, sounds sterile and clinical. But harmonic-rich tones sound full, alive, musical. Nature understands this deeply, even if unintentionally. Birdsong, for instance, is built on harmonics. Many birds, especially songbirds like thrushes and warblers, produce sounds with complex harmonic structures. These songs aren't just for show. Birds use them to claim territory, attract mates, and communicate across distances. Each species has its own repertoire, and within a species, individual birds may have personal variations, something like regional dialects. The mathematical structure of these songs is fascinating. Some species even change their tune depending on the environment. In dense forests, lower-pitched, slower songs travel better through thick vegetation. In open spaces, high, fast notes carry farther. This is called acoustic adaptation, and it shows how even the forest floor has its own set of acoustical equations. Frogs are no slackers either. On warm summer nights, you might hear an entire chorus of frogs calling out across a pond, each species singing in a slightly different frequency range. This isn't just coincidence, it's strategy. If two species had identical calls, the signal would get muddled. By separating their calls into distinct frequency bands, frogs avoid overlap and ensure their messages get through. It's a kind of sonic social distancing enforced by evolution. Insects take this even further. Crickets, katydids and cicadas use chirps, buzzes and clicks to communicate, often at ultrasonic frequencies. Some even use rhythm, producing patterns that repeat with mathematical regularity. And humans, of course, have long drawn inspiration from these rhythms, imitating them in drums, stringed instruments, and songs that echo through time. But not all natural sound comes from living things. The ocean is its own musician. Stand near the shore, and you'll hear the rise and fall of waves, an eternal rhythm that's both chaotic and strangely consistent. Ocean waves are physical manifestations of energy moving through water, shaped by wind, tides, and the contours of the seafloor. The frequency and amplitude of these waves follow mathematical principles too, from simple sine waves in calm waters to complex interference patterns during storms. When waves overlap, they can amplify each other, creating a phenomenon called constructive interference, or they can cancel each other out, destructive interference. Surfers, sailors, and scientists all study these patterns to understand wave behavior, predict dangerous conditions, and even harvest energy from the sea. There's also something called resonance, a phenomenon where a system vibrates more strongly at certain frequencies. Imagine pushing a child on a swing. If you push at the right moment, the swing goes higher. That's resonance. Every object has a natural frequency at which it vibrates most easily. Hit a wine glass with just the right pitch, and it might shatter. That's the result of resonance amplifying the sound waves until the glass can't take the stress. You'll find resonance in everything from bridges to brain waves. In music, it helps instruments project sound. In biology, it's part of how our inner ears work. Tiny hairs inside the cochlea respond to specific frequencies, vibrating in tune with incoming sound. The placement of these hairs along the spiral of the cochlea determines which pitch they're sensitive to. Low frequencies at one end, high frequencies at the other. Your ear is, quite literally, a biological equalizer. Even silence isn't entirely silent. In a quiet room, you might hear your heartbeat, your breathing, the faint hum of electricity in the walls, and beyond that, the brain creates its own noise, a soft electrical symphony of neurons firing in patterns. Some of these rhythms are slow and calming, like the delta waves of deep sleep. Others, like alpha waves, are associated with relaxation and quiet alertness. These brainwave frequencies are measured in hertz, just like sound. It's no wonder that certain sounds soothe us. Think of rainfall, wind through trees, waves crashing rhythmically. These sounds tend to fall within frequency ranges that the human ear finds calming, usually low to mid frequencies without sharp onsets or high-pitched spikes. They mimic the rhythms of the body and the natural world. There's a mathematical serenity to them. Even music therapy uses these principles. Playing tones at certain frequencies, like 40 Hz, associated with gamma brainwaves, has been explored for boosting focus or supporting memory. Binaural beats, which use slightly different frequencies in each ear to create a perceived third tone in the brain, are studied for their potential calming effects. While the science is still ongoing, the idea is clear. Sound affects us deeply, and those effects often follow surprisingly mathematical rules. This connection between math and sound is ancient. The Greek philosopher Pythagoras explored the ratios between musical notes over 2,000 years ago, discovering that harmonious intervals, like octaves, fifths, and fourths, could be expressed with simple numerical ratios. A string half the length of another will produce a note an octave higher. A 2/3 ratio creates a perfect fifth. These ratios aren't just pleasing to the ear, they're etched into the physics of vibrating objects. That's why music is often described as math you can hear. Every chord, every rhythm, every harmony is a pattern, a wave, a frequency dancing through time. Even silence in music has its place. Rests are measured, timed, and purposeful, its structure wrapped in emotion. And the natural world is full of music. whether we're listening or not. Whales sing in low, resonant tones that can travel hundreds of kilometers through water. Elephants communicate using infrasound, frequencies below the range of human hearing. Even trees, when exposed to ultrasound, can emit tiny clicking sounds through their xylem as water moves upward. Sound is not just a sense, it's a signal, a connection, a pattern passed through air and water and wood from one living thing to another, and the rules that shape these patterns, wavelengths, resonance, harmonics, are quietly mathematical. It's comforting in a way to think of the world as always singing. Whether it's a blackbird at dawn or the soft hush of wind over hills, the earth is never truly silent. It's humming, whispering, vibrating with the quiet equations of motion and energy, not random, not chaotic, just beautifully ordered, in a language made not of words, but of waves. And all we have to do is listen. As we draw this quiet journey to a close, it's worth pausing for a gentle breath. We've wandered through spirals tucked into sunflower seeds, followed the branching paths of trees and rivers, listened to the mathematics hidden in birdsong and breaking waves. And all along the way, one truth has echoed softly beneath the surface. Nature is full of patterns, not rigid or mechanical ones, but living, breathing rhythms that whisper of structure, balance and beauty. The math we've explored isn't the kind that demands a calculator. It doesn't live only on chalkboards or inside dusty textbooks. It lives in the way a snowflake forms, the way a bee builds a hive, the way your body rests and wakes with the turning earth. It lives in the curves of shells, in the slow growth of roots beneath our feet, in the flutter of starlings and the stillness of mountains. What we find, again and again, is that complexity doesn't require complication. Often, the most intricate patterns come from simple rules repeated with care, like a fern unfolding or a river choosing its path. Order and chaos don't sit on opposite ends of a scale. They hold hands, they dance together. A murmuration of birds, a thunderstorm, a perfectly timed nap. They all exist where structure and spontaneity meet. Perhaps the greatest gift math gives us in nature is the invitation to slow down, to notice, to pay attention not just to the things we see, but to how they fit together. The way branches echo one another, the rhythm of footsteps on a forest trail, the pulse of your own breath, quietly keeping time. There's poetry in it all, not just in the words we speak, but in the shapes, sounds and movements that nature writes across the world. And now, as your eyes grow heavier, or your thoughts begin to wander gently elsewhere, let this be a soft place to rest. Whether you're drifting off to sleep or simply resting in stillness, know that the patterns are all around you, steady, calming, quietly carrying on. Before you go, if this gentle exploration brought you a moment of wonder or rest, I would be deeply grateful if you'd give this video a like and consider subscribing to The Sleepy Scientist. It helps others find their way here too, and it means the world to me. And I'd love to know, where in the world are you listening from, and what time is it for you right now? It's always beautiful to see how far these calm little ripples reach. Until next time, sleep well, stay curious, and remember, there is quiet poetry in the patterns if we only take the time to look.